257 feet per second. Altitude 4.3 nautical miles. Downrange distance 3 nautical miles.
So the 25th Space Shuttle mission is now on the way after more delays than NASA cares to count. This morning it looked as though they were not going to be able to get off.
1 minute 15 seconds. Velocity 2,900 feet per second. Altitude 9 nautical miles. Downrange distance 7 nautical miles.
We are having technical difficulties. Please stand by.
Breaking news. We start with sad news. The explosion of the Shuttle Challenger shortly after its launch on Cape Canaveral, taking away the life of 7 astronauts. With this travel, the shuttle would have completed its 10 missions since 1983, when it made its first launch. At 11:88 a.m., the Challenger started travel, then 73 seconds later, the disaster happened. Unfortunately, teacher and space participant shuttle Krishna McAuliffe, winner among 11,000 applicants, died, with also Gregor Jarvis, Judy Reshnick, Dick Scooby, Ronald McNair, Michael Smith, and Ellison Onizuka. NASA's salvage team expected several weeks to recover all the pieces in order to find out what went wrong, and there's no hope on finding the crew alive. Flight controllers here are looking very carefully at the situation. Obviously, a major malfunction can be heard from NASA's mission control just after the terrific explosion. Now we connect with Santiago, who's there reporting live.
That's right, Andres. At this very moment, it is said that debris is still falling down from the skies because of the explosion, making it difficult for search effort to begin and to see what can be salvaged and learn what happened to the crash. Mission control, we saw how mission control went silent as the shuttle explodes in the skies, in shock of what we all just witnessed. It happened just approximately 1 minute after the launch, after it took off, and NASA has said it appointed a committee to begin analyzing and investigating with the best scientists what could have gone wrong. Hundreds of spectators in Florida watched as the space shuttle exploded in the skies, sadly after just applauding to a successful launch of the shuttle. Among those people were the families of the crew members who had to watch how the space shuttle exploded and went into pieces. At one moment there was hope that the crew could have survived as a parachute came down from the skies. You could see the parachute coming down. Sadly, NASA came out to say that nothing could have saved the crew members. There wasn't escape pods and neither ejecting seats. Nothing could have saved the crew members. Nicolas is on site at Cape Canaveral with the spectators after what they just witnessed, and he's going to tell us more, so let's go with him.
Thanks, Santiago. We're here on the scene of the accident. As my colleague just stated, a giant explosion coming from the space shuttle was seen minutes ago. Distinctive puffs of increasingly blacker smoke were recorded between 0.8 to 2.5 seconds. The smoke appeared to puff upwards from one of the joints. The multiple smoke puffs in this sequence occurred at about 4 times per second, approximating the frequency of structural load dynamics and a resultant joint flexing. Computer graphics applied to NASA photos from a variety of cameras in this sequence again placed the smoke puffs origins from around 270 to 310 degrees sector of the original smoke spurt. We're still on the lead of discovering the cause of this catastrophe. Unfortunately, none of the passengers of the aircraft survived the incident. Our prayers go to those families of the people involved in the accident. We have been in contact with some of the NASA workers involved in the manufacture and launch of the aircraft, who have informed the newscast of the most probable cause of the accident. According to some of the NASA workers in charge of the construction of the space shuttle, the main possible cause of the implosion of the aircraft surrounding the specifics of the accident will be stated by the following NASA worker, Mateo. The aircraft can be regarded to a failure of the O-ring, which is also known as the sealer of this aircraft, which many factors point out to be due to the unbearable cold temperatures that may have reduced the efficiency of the sealer at the time of the flight. More information surrounding the specifics of the accident will be stated by the following NASA worker, Mateo.
We're sorry about this disaster. After recollecting every piece from the Challenger and many investigations, we have found first the temperatures dipped below freezing, and some of the shuttle engineers were concerned about the integrity of the seals and the solid rocket boosters in such low temperatures. So the loss of the Space Shuttle Challenger was caused by a failure in the joint between the two lower segments of the right solid rocket motor. The specific failure was the destruction of the seals that are intended to prevent hot gases from leaking through the joint during the propellant burn of the rocket motor. The evidence assembled by the Commission indicates that no other element of the Space Shuttle system contributed to this failure. Otherwise, the most possible factors after the investigation was that O-ring resiliency is directly related to its temperature, taking into account the lower temperatures on this day. At first, a warm O-ring that has been compressed will return to its original shape much quicker than with a cold O-ring when compression is relieved. Thus, a warm O-ring will follow the opening of the tank to clevice gap. A cold O-ring may not. Also, we must consider that a compressed O-ring at 75 degrees Fahrenheit is 5 times more responsive in returning to its uncompressed shape than a cold O-ring at 30 degrees Fahrenheit. Finally, as a result, it is probable that the O-rings in the right solid booster at field joint were not following the opening of the O-rings in the right solid booster at field joint were not following the opening of the gap between the tank and clevice at time of ignition.
Thank you, Mateo, for the information. We have received 4 statements regarding the malfunction of the material and the space shuttle itself. The first statement goes as follows. At the cold launch temperature experienced, the O-ring will be very slow in returning to its normal rounded shape. It will not follow the opening of the tank to clevice gap. It will remain in this compressed position in the O-ring channel and will not provide the space between itself and the upstream channel wall. Thus, it is probable that the O-ring will not pressure agitated to the seal gap in time to preclude joint failure due to blow by and erosion from hot combusting gases. One of the other statements was that, on the other hand, no previous high-stress test regarding extreme temperatures were realized before the official launch of the space shuttle. Thank you, listeners, for staying by for the news. We'll keep you updated with any advances that happen in the next hours.